I was at In-N-Out Burger looking at the menu, and it occurred to me that it was an awesome example to introduce systems of simultaneous equations where you have um, multiple variables that you're trying to solve for and multiple equations relating those variables. In this case, it's the In-N-Out menu, so they've got a hamburger, a cheeseburger, and a double-double, which is 2 patties and 2 pieces of cheese. So let me show you the menu. Here's the In-N-Out menu. You can get a hamburger, which has a bun, the spread, lettuce, tomato, and onions, and a beef patty, and that's 390 calories. Or you can get a cheeseburger, which has the bun, the spread, the vegetables, the patty, plus a piece of cheese for 480 calories. Or you can get a double-double, which has 2 beef patties and 2 pieces of cheese for 670 calories. So given this information, how do we solve for how many calories are the cheese, the patty, and the bun and the spread? So the first part is pretty easy. We have the cheeseburger equation, and we subtract the hamburger equation. So it's pretty clear. The hamburger has everything except the cheese, so if we just subtract it from each other, we can immediately solve that the cheese is 90 calories. 480 minus 390 is 90 calories. We're just taking the cheeseburger equation, and we're subtracting the hamburger equation from it, and we get the cheese part of it. Now we go to solve for the beef patty. So we take the double-double equation, which is 2 beef patties and 2 pieces of cheese, and we plug in, we just solved that the cheese was 90 calories, so we plug that into this equation. 2 pieces of cheese are 180 calories, so we plug in 90, and then we subtract 180 calories from both sides of the equation. So that gets rid of the cheese, and you subtract 180 from 670, and you get 490. So now you get 2 patties and the bun and stuff is 490 calories, and now we subtract the hamburger equation from that. So the bun cancels, one of the patties cancels, and we're left with 1 patty, and 490 minus 390 is 100. So 1 beef patty is 100 calories. So now we're making some progress. So now if we go back to the hamburger equation, we've got the bun plus the spread plus the vegetables plus the patty is 390 calories. We just solved that the beef patty was 100 calories, so we plug that in, and then we subtract 100 from both sides. So we get the bun plus the spread plus the vegetables is 290 calories. So that's actually the most caloric aspect, even more so than the cheese or the patty. So now let's check our work. So what we found out was that the bun plus spread plus vegetables were 290 calories, the patty was 100 calories each, and the cheese was 90 calories each. So let's plug that in and see if we get a consistency. So the hamburger is the bun, 290, plus the patty, 100. We get 390, which matches what the menu says. Check. Now let's check the cheeseburger. 290 plus 100 plus 90 equals 480, which is exactly what the menu says. Now let's check the double-double. 290 plus 2 times 100, 2 beef patties, plus 2 times 90 for 2 pieces of cheese equals 670, which is what the menu says. So we checked our answer and we found that we're in fact correct. We were able to solve for 3 components. Notice we don't have enough information to solve for like the spread and the vegetables individually and the bread individually. We had to group them all together. And presumably the vegetables aren't very caloric, but the spread and the bun are very caloric. So if you wanted to minimize your calorie consumption, for example, perhaps you wouldn't eat those parts. So there was a really cool example of solving a system of simultaneous equations with 3 variables and 3 equations. The 3 variables were the bun and the spread, the beef patty and the cheese, and the 3 equations were the hamburger equation, the cheeseburger equation, and the double-double equation. And with that, we were able to solve for the individual components. And so in supercomputing, solving systems of equations is something that's very pervasive. In fact, The way they measure the fastest supercomputers in the world is they use this thing called LinPack. It's a linear algebra program that's essentially doing this. Well, the technique they use to solve the equations is quite different, but they're solving a system of simultaneous equations to measure the speed of a supercomputer. So there's this really cool website called top500.org that lists the fastest supercomputers in the world, and they're basically like solving gigantic versions of this Hamburger equation and stuff like that. It's not exactly true because they don't use the method that we used here. The method we used here is kind of like Gaussian elimination, and that doesn't tend to work out very well on computers with like millions or billions or trillions of unknowns. They use different numerical techniques, but this is a very pervasive technique in numerical algorithms and supercomputing, modeling the world. Typically you turn a partial differential equation into some kind of linear algebra, linear system where you're doing this thing. So it's used all the time. It's very important, and this is sort of a gentle introduction, perhaps the first introduction to this subject. Thank you very much.